Hi, I'm Professor Goins, and welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in college mathematics courses, you're in the right spot, so go ahead and hit the subscribe button, and let's get into the current video. I want to take a look at a Weierstrass substitution. What I'm going to do is I'm going to do this over a sequence of two videos. The first one, I'm going to talk about what the substitution consists of, and then in the second part, I'm going to do examples of integrations using a Weierstrass substitution. Let me give the general idea first. What we're going to do is we're going to see how to take an integrand that consists of trig functions, so an integrand with trig functions, and we are going to, using the Weierstrass substitution, we are going to convert that to another integrand with an algebraic expression. So I'm going to convert an integrand with trig functions to an integrand with algebraic functions, and the idea that really makes this useful is the fact that an integrand with algebraic expressions, we have more techniques available. Well, if there's more techniques, then there's a good chance that we might be able to actually compute the integral as opposed to the integral with the trig functions. So let's go ahead and take a look at what this looks like. What we do, here's the starting point, is I'm going to let t equal the tangent of x over 2, right? If my original integral with trig functions has the variable x in it, I'm going to make this substitution. T is going to, which is my new variable, is going to be the tangent of x over 2. And sometimes this method, if you look up in other textbooks or other YouTube channels, they might call this the half angle, the tangent half angle substitution. I'm going to refer to it as the Weierstrass substitution. Well, what I want to do then, if I have t as tangent of x over 2, remember that my integrand that I'm starting with is going to have like sine of x and cosine of x and tangent of x, things like that. How can I come up with an expression in the variable t if for, say, sine of x? If t is tan x over 2, what's sine of x equal to? Well, we also are going to need, of course, the differential dx. So what I'm going to do is, from this starting point, let's develop the rest of the components for the substitution. If I take this equation right here and I solve this for x, take the arctan of both sides and multiply by 2, that's going to give me x is equal to 2 arctan of t. Right? Take arctan of both sides, multiply by 2. Then from here, the differential dx is going to be equal to, well, it's 2 times, remember the derivative of arctan is 1 over 1 plus the square of the argument, and then of course the differential dt. And so I'll just kind of clean that up a little bit. Therefore, when I do my substitution, I'm going to replace dx with 2 over 1 plus t squared dt. So this is the substitution for the differential in the original integral. Now from here, let's go ahead and find, say, the sine and the cosine. Let's do the cosine first. Now, here's what I'm going to do in order to find the sine and the cosine is let's use this expression right here, this original substitution, to create a triangle. So create a triangle, and again the argument of the tangent function is going to be my angle, so that means that this would be x over 2, and remember the tangent is the opposite over the adjacent, so that means that this would be a t and this would be a 1, so t over 1 of course is t, and then using the Pythagorean theorem, of course the hypotenuse would be the square root of t squared plus 1. Now from this I can find the sine and the cosine of x over 2. In particular, I can find that the cosine of x over 2 is, again, remember cosine is adjacent over the hypotenuse, so that means that this would be 1 over the square root of t squared plus 1. And the sine of x over 2, which would be opposite over hypotenuse, would be the t over the square root of t squared plus 1. Okay? Now, these building blocks are then going to allow me to find the sine and the cosine of x. To find the sine and the cosine of x, we're going to use some trig identities. First and foremost, the double angle for the cosine. So cosine of, let's use the variable theta. Cosine of 2 theta is equal to cosine squared theta minus sine squared theta. All right? And the idea is that this angle right here, this argument is simply twice these ones. In other words, if I was to say cosine of just x, this would be the same thing as cosine squared of, well, notice that this, or let me say it this way, this angle is twice this one, so this is half of this one. That means that in this expression here, I would have to replace this with half of this. So x over 2, and then minus sine squared of x over 2. And of course, we have the expressions for sine and cosine of x over 2 over on the other side of the board. And therefore, I would get 1 over the square root of t squared plus 1 squared minus t over the square root of t squared plus 1 squared. And then, let's put this down here. We have the cosine of x. Well, of course, if I square this, the top is going to be 1. The bottom is just going to get rid of the square root. Over here, the top is going to be t squared, and then I'm going to get the square root on the is going to get eliminated on the bottom. And of course, the denominators match, so I can subtract the numerators, giving me 1 minus t squared over t squared plus 1, or 1 plus t squared. And this right here is going to be what I will replace the cosine with. Again, remember at the beginning I said that trig expressions are going to turn into algebraic expressions. Notice here this isn't 2 over 1 plus t squared is a rational function, as is this one. Therefore, I am going to create algebraic expressions. Similar to what I just developed up here, let's do the same thing for the sine function. All right, so for the sine, again, I'm going to have to relate sine of x over 2 with the original sine function, and therefore I'm going to, again, use a double angle identity. Remember that the double angle for the sine function is the sine of an angle, or sine of twice the angle, sine of 2 theta, is 2 sine theta cosine theta. Okay, so sine of 2 theta is 2 sine theta cosine theta. Repeating the same sort of discussion that I had up here, we can say this differently, and that these two angles right here are simply half of this one, or this one is double these, right? That means if I was to replace 2 theta with x, sine of x is going to be equal to, well, notice that this would be 2 sine x over 2, and then cosine of x over 2. Okay? So sine of x would be 2 sine x over 2, cosine x over 2, and again, I can replace this sine of x over 2 with this expression and cosine of x over 2 with this expression, which would give me then the sine of x in terms of t. That's going to give me 2 times t over the square root of t squared plus 1 times cosine, which is 1 over the square root of t squared plus 1. And then, let's see, I can kind of put this over here in the middle, I guess. We get, well, this is equal to 2t over t squared plus 1. And therefore, I have the sine of x, right, is, of course, equal to this expression right here. And, of course, to get the remainder of the trig expressions, tangent and cosecant, etc., we just take ratios of the sine and the cosine, and that would then give me my entire collection of substitutions that I'm going to use for the Weierstrass substitution. Look for that in the next video where I show you how to use this to compute some integrals. Thank you for watching. Please consider subscribing.